Previously, we looked at how as time passed, the reaction rate forward would decrease, and then the reaction rate reverse would increase. Obviously, this here is our reactant, so we're going to look at our reactant over here. It's big in the beginning and then eventually decreased. Same thing with the reverse reaction. Okay, this is going to be increasing, so that's our product. So that'll be this one over here. It's 0 at the beginning and then eventually increased. Okay, eventually these slopes would equalize. Okay, so their slopes would equal to 0. So now we'll derive the equilibrium constant. Okay, which is the ratio between the concentration of the product and the reactants. Okay, so the K forward is obviously our reactant, which would be our N2O4 over here. So we're just going to put product over here. This would be our reactant over here. Again, this one here was our N2O4, and then our product here, reverse, was the NO2. Okay, eventually they equalized, right? So I'm just going to put an equal sign in between, so they are now equal. So for this K forward, we can do either one, but I'm just going to do K forward instead of the K reverse. It doesn't matter. So for the K forward, this numerator here is going to divide by the denominator so they can cancel. If I do it on the left side, I got to do it on the right side, which I've done, and it equals to this. Okay, whenever we have a concentration, it must be to the power equal to the coefficient. Okay, so our coefficient, this was our chemical equation. We got to balance it. So we're going to put a 2 over here. This 2 NO2 is obviously our product over here. It has to be raised to the power of 2. Okay, whatever the moles is over there. Okay, obviously this one is a 1, so we're just going to keep it as a 1 there. So technically our K, okay, is equal to our concentration of the product over our concentration of the reactant. Okay, this is not KEQ. Okay, if it was KEQ, this would be a permanent equilibrium constant. Right now it is not. It is a temporary equilibrium constant. Okay, because we haven't canceled out our non-pure compounds yet, which we'll look at over here. If we look at this chemical equation over here, it can be represented as this way. Okay, notice how big A, B, C, D is represented by the concentrations, and then small a, B, C, D is represented by the moles. Okay, so that's the superscript to the coefficient. Notice how the equilibrium requires both the concentration of the products and the reactants. In rate law, we only dealt with the concentrations of the reactants. Okay, see the links in the description below. Okay, for rate law and rate law practice questions, we've only dealt with reactants. Okay, once we find our KEQ, our permanent one, if it's greater than 10 to the 10, it goes to completion. If it's less than 10 to the negative 10, there is no reaction. We only have reactants in the container, and then KEQ is equal to 1 means that they are the same. Okay, let's have a look at this question over here. We have to balance it out. 2 over here. This is obviously a solid state, and we're just going to follow this equation that we've done, our temporary equilibrium constant. Okay, so we're going to obviously have our 2's over here, 2's over here, 1's over here. I want to get rid of all of the solids and the liquids because they're pure, they're constant, they're going to be integrated within the K. We have to cancel them out. We're only going to be left with the gases. Okay, so obviously this one over here, I'm just going to put it on the right side over here on the bottom. That way they're diagonal so that they can cancel. This one over here, I'm going to put up here so that it can be diagonal, that they can cancel as well. So this one cancels out, this one cancels out. If I do this on the right side, I got to do it on the left side. So my KEQ permanently is this answer. This here is the green question of the day. Please give this a try on your own. I'll be giving you the answers shortly. This is the answer.